Confidence intervals for estimating the population mean. The formulas that we use to estimate the population mean completely depends upon our sample size and whether the population standard deviation is known. Our first case is a large sample case, which means that our n value is greater than or equal to 30 and sigma is known. The concept of whether sigma is known is often a point that confuses students. Knowing something about an entire population is huge information. Therefore, in a problem, they would always specify that the population standard deviation is known. If you encounter a problem and the problem simply states that the standard deviation is this value, I would automatically assume that that is sample standard deviation. Again, if they knew something that large about an entire population, they would definitely mention that inside of the write-up for the original problem. So, for the sake of determining whether sigma is known, your problem should either say sigma is equal to this value, or they should say the population standard deviation is this value. So in the absence of either of those keywords, you should assume that sigma is not known in a problem. So for a large sample case with sigma known, our confidence interval formula is given here on the slide. The formula is x bar plus or minus z alpha over 2 times sigma over the square root of n. 1 minus alpha we will refer to as our confidence coefficient. Up to this point in this course, everything in this formula should be very familiar to us except for the concept of z alpha over 2. In a previous section, we learned how to compute a sample mean. N is simply the size of the sample, and for this case, sigma would actually be given. For our second case, if you have a small sample case with a normal population and sigma is known, we use the same formula. We should note that for a large sample case, it is not necessary that we know that the original population is normal, because the central limit theorem allows us to assume that x bar is normally distributed. However, for a small sample case, we do not have the central limit theorem to stand on. Therefore, in order for us to use this formula with a small sample case, we must know that the original population was normally distributed. So for case 2, we have a small sample case with a normal population and sigma known. And for this case, we use the same formula as on the previous slide. As mentioned on the last slide, the only thing that is foreign to us, or the only thing that should be foreign to us at this point, is the concept of computing a z alpha over 2 value. For this reason, we have distinct steps that I've outlined on this slide to help us compute z alpha over 2. We're defining z alpha over 2 as the z value with the upper tail area of alpha divided by 2. In order to compute this measure, we start by computing alpha, which is equal to 1 minus our confidence coefficient. In step 2, we compute alpha divided by 2. And in step 3, if we have an upper tail area of alpha divided by 2, in order for us to use the standard normal charts, we have to know the area to the left of that z-score. So if the upper tail area for the z-score is alpha divided by 2, then the area that we can look up on the chart would be equal to 1 minus alpha divided by 2. For this reason, in step 3, we compute the area 1 minus alpha divided by 2. In step 4, we go to the area section of the cumulative standard normal table and find the area as close as possible to the area that we computed in step 3. The corresponding z value is our z alpha over 2 value. Before we even begin to become overwhelmed by the different formulas, let's apply it to an example so that I can show you that it's really not that difficult to apply. A research group wanted to determine the average price of regular gas in North Carolina. A sample of N equals 25 gas stations in North Carolina provided a mean of $3.35 with a population standard deviation of 25 cents. Construct a 90% confidence interval for the mean price of gas in North Carolina. Assume that gas prices are normally distributed. So for our problem, our N value is 25, sigma is 0.25, and the sample mean is 3.35. Since our N value is 25, we have a small sample case. The problem tells us that our population is normally distributed, and sigma is given in this problem. Therefore, this is a small sample case with a normal population and sigma known, or case 2 outlined on the previous slide. So we can use the formula x bar plus or minus z alpha over 2 times sigma over the square root of n in order to construct a 90% confidence interval. In order to find z alpha, we start by computing alpha as 1 minus 0.9. We have 0.9 as our confidence coefficient because we are trying to construct a 90% confidence interval. So 0.9 is our confidence coefficient. So alpha for this case is equal to 0.1. In step 2, we compute alpha over 2, 0.1 divided by 2, and obtain 0.05. In step 3, we compute the area that we need to look up on our standard normal table. The area is 1 minus alpha over 2, or for our case, it's 1 minus 0.05, which equals 0.95. And in step 4, we go to the area section of the chart on our cumulative standard normal table and find the area as close as possible to 0.95. For this case, we see that 0.95 is equally close to two different values listed on the table. 0.9495 and 0.9505 are both 0.0005 away. And so since we can't choose one value that is the closest to the area that we want, we see that the value that we want is exactly in between these two areas. Therefore, we should select the z-score that is exactly in between the two z-scores that correspond to these areas. 0.9495 corresponds to a z-score of 1.64, and 0.9505 correspond to a z-score which is 1.65. The midpoint between the z-score 1.64 and 1.65 is 1.645. Therefore, the z alpha over 2 value that we will use is 1.645. Returning to our formula for estimating the population mean, we can now plug in the x bar from our problem, our z alpha over 2 value, our population standard deviation value, and our n value. You should always start by computing the error section of the problem. That's everything after the plus or minus symbol. In doing this, we see that our formula becomes $3.35 plus or minus 0.08 or 8 cents for this problem. So working this section out, you should get 0.08 or 3.27 to 3.43 is our interval. We obtain 3.27 by saying 3.35 minus 0.08, and we obtain 3.43 by computing 3.35 plus 0.08. We are 90% confident that the true population mean, that's saying if you were to sample all gas stations in North Carolina instead of the small sample of 25, you would not obtain an average price of exactly $3.35 as we obtained in our sample. However, we are 90% confident that if you were to sample all of them, the true population mean gas price would be between $3.27 and $3.43. So this is providing an estimate for the population parameter. Example 2. An Android application creator wants to identify the average age of its customers. A sample of 49 customers is taken. The average age in the sample was 22.5 years, with a population standard deviation of 5 years. Construct a 95% confidence interval for the true population mean age of its customers. For this problem, our n value is 49, and since they distinctly said the population standard deviation, we know the symbol for the population standard deviation is sigma, and that's equal to 5, and our sample mean was equal to 22.5. For this problem, we have a large sample case, n is greater than or equal to 30, and sigma is known. Therefore, this is case 1, and we can use this formula in order to compute our 95% confidence interval. The steps for computing z alpha over 2 for our problem. We start by computing alpha. Alpha is equal to 1 minus our confidence coefficient. In this problem, we want a 95% confidence interval. Therefore, our confidence coefficient is that percentage in decimal form. Our confidence coefficient for this problem is 0.95. Therefore, alpha is equal to 1 minus 0.95 or 0.05. Alpha divided by 2 is 0.05 divided by 2, which equals 0.025. In step 3, we compute the area that we have to look up on our standard normal table. The area is equal to 1 minus alpha over 2. For our case, that's 1 minus 0.025, which equals 0.975. In step 4, we go to the area section of our standard normal table to find the area as close as possible to 0.975. When we go to the standard normal table, we find on this table 0.975 exactly, and it's in the row for 1.9 and the column for 0.06. Therefore, the corresponding z-score to this area is 1.96. So returning to our formula for computing the confidence interval for our problem, we can fill in our sample mean value, our z alpha over 2 value, our sigma value, and our n value for this problem. If we compute the error section of this problem, we'll obtain 1.4. So we estimate that the population mean is 22.5 plus or minus 1.4. If we subtract 1.4 from 22.5, we obtain 21.1. If we add 1.4 to 22.5, we obtain 23.9. Therefore, we can state that we are 95% confident that the true population mean age of their customers isn't exactly 22.5 like we found for our sample, but we're 95% confident that it is between 21.1 and 23.9. Now let's get some hands-on practice. You should begin by reading this scenario on this slide, determining whether we have a large sample case, whether our sigma value is known, and only if needed, whether our population is normally distributed. We only need to know about the population being normally distributed if we have a small sample case. You should pause the video at this time and try to complete this problem. You should have identified that this is case 1, a large sample case with n equals 49 and sigma being known. You should have used the formula x bar plus or minus z alpha over 2 times sigma over the square root of n in order to estimate your population parameter. In computing z alpha over 2 for a 99% confidence interval, you should have computed alpha as 0.01, alpha divided by 2 as 0.005. The area that you should look up in the chart should be 1 minus alpha over 2, or 1 minus 0.005, which equals 0.995. You should then have went to the standard normal table to try to find the area as close as possible to 0.995. When you went to the chart, you should have found two values that were equally close to the value 0.995. 0.9949 and 0.9951 are both 0.0001 away from our desired value. Their corresponding z-scores are 2.57 and 2.58. Therefore, the z-score that we want is exactly in between these two values. The z-score in the middle of these two values is 2.575. Now, returning to our confidence interval formula, we can plug in our x bar value, our z alpha over 2, our sigma, and our n value. Computing the error section of this problem, we obtain 1.18. So our confidence interval should be formed as 31.5 plus or minus 1.18. This gives us the confidence interval 30.32 until 32.68. So we can state that we are 99% confident that the true population mean miles per gallon for the vehicle is between 30.32 and 32.68 miles per gallon.